Hi and welcome to Trigonometry video 4. In this video we'll be looking at exact ratios. We'll develop the exact ratios for some special angles in triangles, and we will, as part of that, review your basic understanding of surds. So let's start with our triangle here on the left hand side. Now in this triangle I'm going to pass on some assumptions. It's not to scale, but let's assume it's an equilateral triangle and therefore it has side lengths 2, 2, 2. I've chosen 2 arbitrarily, but there's a very particular reason why I've chosen 2. Now let's drop a perpendicular line that will meet the base at a right angle, and of course we'll split the base in half. And so if it splits the base in half, that means that each side is now 1 and 1. And so now we have this new triangle. And let's just take it out over here so we can look at it. And this new triangle looks like this. This is obviously a slightly rougher drawing, but you can see that this is 2, this is 1, and it's a right angled triangle. Now of course this was originally an equilateral triangle, which means that this side, this angle here is 60, so this angle here is 60, and this top angle therefore must be 30. And we have 30, 60 and 90 makes 180. Now moving on from this, we really want to know what this side is equal to. So to calculate the value of that side, we do a little bit of Pythagoras theorem. 2 squared should be equal to 1 squared plus, and we'll call it x squared. Rearranging, we get x squared is equal to 4 minus 1, and so x is equal to the square root of 3. Now typically it's plus or minus the square root of 3, but because this is a length, we're going to have to deal with the square root of 3. So I'll write down there the square root of 3. And there's our exact triangle. So let me show you what comes out of that exact triangle and formalize a little bit for you. So my exact triangle looks like this. I know the side lengths and I know the angles. 60, 30, root 3, 2 and 1, and it leads to these common ratios. So let's start with the 30 first of all. Sine of 30 is equal to opposite over hypotenuse, which is 1 over 2. Cos of 30 is equal to adjacent over hypotenuse, which is root 3 over 2, and of course tan of 30 is equal to opposite over adjacent, which is 1 over root 3. Or, because we need to rationalise the denominator in some surd cases, root 3 over 3. Either of those is fine. And now let's look at the 60 case. Sine of 60 is equal to opposite root 3 over 2. And cos of 60 is equal to adjacent 1 over hypotenuse, which is 2. And tan of 60 is equal to opposite over adjacent, which is root 3 over 1, or just root 3. And there we have our 6 exact ratios that come from that particular triangle. It's really interesting to note here that tan really becomes a bit of a standalone entity from now on. It's important, it works in a lot of contexts well, but it doesn't really relate to sine and cos in the same way as they relate to each other. There is a relationship there which you'll explore later, but sine and cos is really interesting. Sine and cos interchange. And I won't go through too much detail of the exact interchange, but you'll start to see some really nice symmetry there between sine and cos. Sine of 60 is equal to cos of 30, and cos of 60 is equal to sine of 30. Now let's move on and talk about a second special triangle. Let's say that this triangle here is a right angle triangle, and it's isosceles, so I'll give it side lengths 1 and 1. Now, using Pythagoras theorem, I can get that x here, x squared is equal to 1 squared plus 1 squared, which is equal to 2, and x is equal to the square root of 2. So I have a square root of 2 here. And of course, because it's isosceles, these angles are equal, so this angle is 45, as is this angle. And this leads to a new set of exact ratios, which I'll just add to the bottom here. First of all, sine 45 is equal to opposite 1 over root 2, which is the hypotenuse. And of course we can write that with a rational denominator by writing it as root 2 over 2. And cos of 45 is equal to adjacent 1 over hypotenuse, root 2. So that's also 1 over root 2 or 2 root 2 over 2. And of course, last of all, you'll see this green box is getting a little bit in the way. Tan of 45 is equal to opposite over adjacent, which is 1 over 1. And tan itself has some really nice properties. So there's your exact ratios. They are really the ones you need to know. Outside of that, as you get into trig functions and start working more with trig functions and trig equations, you'll also want to know sine of 90 and sine of 0 and cos of 90, etc., and start to build that. You want to build relationships between sine and cos and also how tan fits into it, and then you'll start looking at angles outside the scope from 0 to 90. Here's a little bit of a summary for you. You may wish, of course, to pause the video here and just copy this slightly neater version down.